You wake up, you flip the light switch, the room fills with light. Simple, obvious. You've done it 10,000 times. You think you know what happened. Electrons started flowing through the wire, like water through a pipe. The electricity traveled from the wall, through the cord, into the bulb. The bulb got power. Light came out. That's the story they told you in school. Voltage is like pressure. Current is like flow rate. Resistance is like friction in the pipe. Here's the thing. That story is wrong. Not approximately wrong. Not slightly misleading. Fundamentally, deeply, structurally wrong. The electrons in that wire barely moved, maybe a millimeter per second. If electricity really traveled by electrons walking through copper, it would take hours for your light to turn on, but it turned on instantly. So what actually happened? This is where it gets strange. The energy that lit your bulb didn't travel through the wire at all. It traveled around the wire, through the empty space surrounding the copper. The wire is just a guide, a boundary condition. The real action happens in what you'd call nothing. You're thinking that can't be right. I can see the wire. The wire is connected. The electricity must go through the wire. Stop. Let me show you what electricity actually is. And I promise you, by the end of this, you will never look at a light switch the same way again. Think back to when you learned about electricity. Maybe middle school, maybe high school. Your teacher drew it on the board. Electrons are like water molecules. Voltage pushes them. Current measures how many flow past a point each second. This model works for basic calculations. Ohm's law, series and parallel circuits. It gets you through the exam. But it hides something essential. It hides what electricity really is. Think about what happens when you turn on a faucet. The water that comes out was sitting in the pipe all along. It had to travel from the water tank, through the pipes, and out to you. That takes time. So here's a question. When you flip a light switch, how long does it take for the light to come on? If electrons had to flow from the power plant to your house like water through a pipe, you'd be waiting. The wire might be miles long. Electrons would need to travel that entire distance. But the light turns on instantly, not almost instantly, instantly. How fast do electrons actually move in a wire? I'll tell you, about 1 millimeter per second. That's slower than a snail. At that speed, it would take an electron roughly half an hour to travel across your living room. But your light turns on in a fraction of a second. Something is very wrong with the water pipe story. Let me make this concrete. Inside a copper wire, there are electrons, lots of them. Copper has about 8.5 times 10 to the power of 28 free electrons per cubic meter. That's an enormous number. The wire is already packed with electrons before you do anything. When you close a circuit, you don't inject new electrons into one end and wait for them to come out the other. The electrons are already there, all of them, throughout the entire wire. What happens is more like a line of people standing shoulder to shoulder. If you push the person at one end, the person at the other end feels it almost immediately, not because the first person walked down the line, but because the push was transmitted through the crowd. The individual electrons barely move. They drift slowly, very slowly, but the effect travels fast. Here's the thing though, that's still not the real story, because the push isn't traveling through the electrons. Not really. The push is traveling through something else entirely, something invisible, something that exists in the space around the wire. And this is where your entire picture of electricity needs to collapse. Stop thinking about the wire for a moment. Think about the space around the wire. When you close a circuit, something happens in that space. An electric field forms. A magnetic field forms. These fields exist outside the wire, in the air, in the vacuum, everywhere around it. And here's the secret. Nobody tells you in school. The energy doesn't travel inside the wire. The energy travels in the fields outside the wire. Read that again. The copper wire is not a pipe carrying energy. The copper wire is more like a guide. It shapes the fields. It directs them. But the actual energy, the thing that powers your light bulb, that energy is flowing through empty space around the wire. There's a precise mathematical description for this. It's called the pointing vector. It points in the direction energy flows. And when you calculate it for a simple circuit, you find something shocking. The energy flows from the battery through the space around the wires and into the light bulb. It doesn't flow through the wires at all. The electrons in the wire, they're just responding to the fields. They're not carrying energy down the line. They're being pushed by fields that already exist throughout the circuit. This is why the light turns on instantly. The fields propagate at nearly the speed of light. The energy doesn't wait for electrons to drift. The fields set up almost immediately, and the energy flows where the fields direct it, through space, not through metal. Your entire mental model was backwards. Now I need to tell you something that should completely restructure how you see the world. The electromagnetic force, the force behind electricity, is not some specialized thing that only happens in wires and power plants. It is the dominant force in your entire life. Everything you see, everything you touch, everything you feel, almost all of it is electromagnetic. Let me prove it. Push your hand down on a table right now. Go ahead. Push hard. Why doesn't your hand go through? You'll say the table is solid. Wrong. That's just a label. That doesn't explain anything. You'll say the atoms are packed together. Better. But keep going. Why don't the atoms in your hand pass through the atoms in the table? Here's the truth. Atoms are mostly empty space. If you scaled an atom up to the size of a football stadium, the nucleus would be a pea at the center. The electrons would be tiny specks near the seats. Everything in between is nothing. Your hand is empty space. The table is empty space. So why can't they pass through each other? Electromagnetic repulsion between electrons. The electrons in your hand have negative charge. The electrons in the table have negative charge. Like charges repel, they push away from each other with enormous force. When you press on the table, you're feeling trillions of tiny electromagnetic battles. Electrons refusing to overlap, pushing back against each other through empty space. You've never touched the table. Not really. There's always a tiny gap, a distance where the electromagnetic repulsion becomes strong enough to stop you. What you call contact is just electromagnetic force acting at very small distances. And here's the connection. The force stopping your hand at the table surface is the exact same force that makes magnets push apart, the exact same force that makes lightning strike, the exact same force powering your phone. Same force, just different scales, different configurations. You didn't realize you were surrounded by electricity because you only recognize it when it's unfamiliar. When magnets push through visible air, that seems strange. When your hand stops at a table, that seems normal, but it's the same physics, the same fundamental force. Let me give you a number that will break your brain. The electromagnetic force is about 10 to the power of 36 times stronger than gravity. That's a 1 followed by 36 zeros. Gravity, the thing that holds planets in orbit, that keeps galaxies together, that seems so powerful and inescapable. It is almost nothing compared to electricity. Between two electrons, gravity is so weak it might as well not exist. The electromagnetic repulsion completely dominates by a factor that's beyond human comprehension. So here's the question that should keep you up at night. If electricity is that strong, why isn't everything exploding? Why don't atoms tear themselves apart? Why doesn't matter disintegrate? Why can you sit calmly in your chair instead of being ripped to pieces by forces trillions of times stronger than anything you've ever imagined? The answer is almost magical. Cancellation. Think about what an atom actually is. At the center, you have protons, positive charge. Around that, you have electrons, negative charge, positive and negative, plus and minus. These charges follow one simple rule: like repels like, opposites attract. And here's the key: the forces are exactly equal in magnitude. A proton attracts an electron with exactly the same strength that it would repel another proton. So in normal matter, you get an intimate mixture of positive and negative charges. Protons and electrons packed as close together as physics allows. Every positive charge surrounded by negatives. Every negative surrounded by positives. And they balance out. The enormous repulsive forces are canceled by equally enormous attractive forces. Everything becomes neutral. The forces are still there. Those monstrous electromagnetic forces are still acting. Every atom in your body is a battlefield of forces stronger than gravity by 36 orders of magnitude. But they're balanced so precisely that the net effect is zero. How precise? Let me tell you. If you and I were standing near each other and we had just 1% more electrons than protons, the repelling force between us would be enough to lift a weight equal to the entire Earth. 1% imbalance, earth lifting force. That's how strong electricity is. That's how perfect the balance must be. In normal matter, the balance isn't 99%. It's not 99.99%. It's perfect to about 1 part in 10 to the power of 25. That's why you don't explode. Not because the forces are weak, but because they cancel with terrifying precision. Now take a piece of plastic wrap, rip off a strip, rub it between your hands really fast, like you're trying to warm them up. Now hold it near the back of your hand without touching. Feel that. The hairs on your arm are moving, standing up, reaching toward the plastic. You can actually feel the plastic pulling on you from a distance. Stop and think about that. You rub plastic. That's it. No batteries, no wires, no power source, just friction. And now that plastic can reach across empty air and tug on your body. How? When you rub that plastic, you scraped electrons off your hands and piled them onto the plastic. Just a few trillion extra electrons. A few trillion sounds like a lot. But compared to the total number of electrons in that plastic, it's essentially nothing. A tiny, tiny excess. But here's the thing. Because the underlying forces are so enormous, even the smallest imbalance creates effects you can feel. You've disturbed the perfect cancellation. You've given the plastic a slight negative charge. And now it's reaching across space, pulling on the positive charges in your arm, pushing on the negative ones. That's the electromagnetic force acting at a distance. The same force that holds atoms together. The same force powering your city. Most people shrug. Static electricity. Learned that in middle school. No big deal. No big deal? You're looking at one of the 4 fundamental forces of the universe, demonstrating its ability to act across empty space. The force that makes chemistry possible. The force that lets your neurons fire and your muscles contract, and you think it's a parlor trick. Let me push this further. Why does wood exist? Why does water exist? Why does anything hold together instead of drifting apart into separate atoms? Chemical bonds. You learned that word. But what is a chemical bond? It's electrons being shared between atoms. Electromagnetic attraction and repulsion, finding a stable arrangement. When hydrogen bonds to oxygen to make water. What's happening is purely electromagnetic. The electrons arrange themselves in a configuration that minimizes the total energy. Attraction's balanced against repulsion. That's it. That's what chemistry is. Chemistry is not a separate subject from electricity. Chemistry is electricity. It's the electromagnetic force acting between electrons in different atoms. Every reaction, every molecule, every material in the universe is held together or torn apart by the same force you felt with that plastic wrap. And biology? Biology is chemistry. Which means biology is electricity. Your neurons fire through electrical signals. Your muscles contract through electrical impulses. The proteins in your body fold into shape because of electromagnetic interactions. You are an electrical being. Your thoughts are electrical patterns. Your heartbeat is an electrical rhythm. Your entire existence depends on the electromagnetic force operating at every level, from atoms to organs. Now let's talk about magnets. You hold two magnets near each other, north to north, they push apart. You can feel the resistance in empty air. This seems different from electricity. This seems like a separate phenomenon. We even give it a separate name, magnetism. But here's the truth. Magnetism and electricity are not two different forces. They're two aspects of one unified force, the electromagnetic force. Where does magnetism come from? Moving charges. When electrons move, when current flows, when charges are in motion, they create magnetic fields. That's it. That's the entire source of magnetism in the universe. The magnets on your fridge, they work because electrons inside the material are spinning. Electron spin is a kind of motion. That motion creates tiny magnetic fields. In a permanent magnet, all those tiny fields align in the same direction and add up. No mysterious magnetic substance, no separate magnetic force, just electrons in motion, creating effects through the same electromagnetic force. And here's something even stranger. Magnetism is actually a relativistic effect of electricity. When charges move, strange things happen to the electric forces between them. Lengths contract, time changes, and what appears in one reference frame as a purely electric force can appear in another frame as a magnetic force. The magnetic force is a small correction to the electric force, a relativistic adjustment that only becomes noticeable when charges are moving. This means that in a deep sense, there is only one force, the electromagnetic force. Magnetism is just what electricity looks like when things are in motion. Let me bring this back to practical electricity. You plug in a lamp, current flows, the bulb lights up. Where does the energy come from? You might say the power plant, and that's true. But how does it get from the plant to your bulb? Here's the picture most people have. The power plant pushes electrons into one end of the wire. Those electrons travel through miles of wire. They arrive at your house. They flow through the light bulb. The bulb converts their energy to light. That picture is wrong in almost every way. The electrons don't travel from the power plant to your house. The electrons in your house wiring were already there. They shuffle back and forth, barely moving. In alternating current, they don't even maintain a direction. They oscillate in place. The energy doesn't travel through the electrons. The energy travels through the electromagnetic fields that surround the wires. When the power plant operates, it creates an electromagnetic disturbance. That disturbance propagates outward through the fields. It travels through space, guided by the wires at nearly the speed of light. The bulb doesn't receive energy from incoming electrons. The bulb sits in a region of space where electromagnetic fields are doing work. The fields push on electrons in the filament. Those electrons collide with atoms. The filament heats up, it glows. The wire is not a pipe delivering energy. The wire is a boundary condition that shapes how the fields behave in space. This is why power transmission works across huge distances with thin wires. The wires don't carry the energy inside them. They sculpt the fields in space. The energy flows around them. I've told you what electricity does. I've told you how it behaves. I've told you about fields and forces and cancellation and relativity. But I haven't told you what electricity is, because nobody knows. What is charge? Why do some particles have positive charge and some have negative? Why do charges create forces at a distance? What is a field, really? These questions don't have answers. Not yet. Maybe not ever. We can describe charge mathematically with perfect precision. We can predict its behavior to 11 decimal places. Quantum electrodynamics, the theory of how light and matter interact, is the most precisely tested theory in all of science. But that doesn't mean we understand what charge is at its core. It's like asking what is mass, really, or what is space, or what is time. At some point you hit bedrock. You reach concepts that can be described and measured, but not explained in terms of anything simpler. Charge might be one of those bedrock concepts. a fundamental property of the universe that just is. This should bother you, and it should excite you. It means we're not done. It means there's still mystery at the heart of the most familiar phenomenon in your life. Every time you flip a switch, you're manipulating something whose ultimate nature remains unknown. Let me tell you what all this means. The lie you were taught wasn't a deliberate deception. It was a shortcut, a useful fiction that gets you through high school physics and lets you wire a house. But it hides something spectacular. Electricity is not a substance that flows. It's not energy traveling through metal. It's not separate from magnetism or chemistry or light. Electricity is a glimpse of one of the four fundamental forces that construct reality itself. The force that holds your atoms together, the force that lets you see, the force that makes matter solid and chemistry possible and life sustainable. It operates at a distance through invisible fields that permeate all space. It's so powerful that it would destroy you instantly if not for an almost miraculous cancellation between positive and negative charges. It unifies phenomena you thought were separate: static shocks and lightning, magnets and motors, chemistry and biology. And beneath all of that, at the very bottom, sits a mystery we cannot fully resolve. What is charge? What is a field? Why does the universe have this structure at all? We don't know, but we can describe it. We can measure it. We can use it to build civilization. That's what electricity really is. Not a utility, not a convenience, a window into the fundamental nature of reality, a force so strange and powerful that even our best theories leave its deepest nature unexplained. So next time you flip a switch, I want you to think differently. You're not sending electricity through a wire. You're setting up electromagnetic fields in the space around you. You're creating patterns of force that propagate at light speed. You're tapping into the same phenomenon that holds your body together and makes stars shine. Next time you push on a table, remember you're not touching it. You're feeling electromagnetic repulsion between electrons, the same force, just at smaller scales. Next time you see a magnet stick to a fridge, don't think of it as a separate mystery. It's the same force, appearing in a different guise, because charges are moving. The world is electric. Everything you experience, except for gravity, is electromagnetic. The forces are always there, always acting, usually canceling so perfectly you never notice. But now you know. Now you can see through the comfortable illusion to the spectacular machinery beneath. That's what physics is for. Not to make things more complicated, but to reveal what was always there, hidden by familiarity. The truth is stranger than the lie, and far more beautiful. Think about this tonight. When you turn off the light, when you plug in your phone, when you feel the cold metal of a doorknob, you're not just using electricity, you're touching the fundamental structure of reality itself.